I have a LTI system, okay, which is causal and stable. Causal and stable. Okay, let me call that as H of Z. Now, a transfer function which has got the same magnitude response and all zeros inside the unit circle. I'm going to call that as H min of Z. The difference between these two, both of them have got the same magnitude response, but this one has got all zeros inside the unit circle. Okay. By the same token, I can also look at a third transfer function which has got the same magnitude response but has got all zeros outside the unit circle. Okay, it will have what the exact opposite. This one has got minimum phase lag, that will have maximum phase lag. So I use the subscript max. So this one has all zeros outside the unit circle. Okay, what about H of Z? It is mixed. Some zeros are inside, some zeros are outside. Okay. However, the magnitude responses for all of them are the same. So, magnitude H E of j omega is equal to magnitude H min E of j omega equal to magnitude of H max E of j omega. And this is true for all omega. Okay. Now, remember Parseval's theorem or Parseval's relation. The Parseval's relation says that if I integrate from 1 over 2 pi minus pi to pi, magnitude H E of j omega magnitude square d omega. Okay, that's the frequency domain component. What will it be in the time domain? These are all causal stable, so start at n equal to 0, n equal to 0 through infinity magnitude H of n magnitude squared. Okay, that's Parseval's relationship. But because all the magnitude responses are the same, this is also equal to summation n equal to 0 through infinity magnitude of H min of n magnitude squared. It's also equal to summation n equal to 0 through infinity magnitude H max of n magnitude squared. All three of them are going to be equal to the same right hand side because that's the Parseval's relationship. Okay, I hope you are comfortable with this particular expression. Okay, now we're going to state the important property. Again, we're going to be using a result, stating a result without going through the details of the proof, but the proof of course is there in Oppenheim and Schaefer. So, partial energy, how do we define that? Partial energy. Okay, for the mixed zeros transfer function, let's call that as E of n. Okay, E stands for energy, n is the first n plus 1 terms. Summation m equal to 0 through n, not up to infinity, only up to the first n up to index n, magnitude H of m magnitude squared. Okay, so similarly you can write down the partial energy for the minimum phase. This will be summation m equal to 0 through n H min of n magnitude squared, and you can write down the partial energy for the maximum phase term. This is summation n equal to m equal to 0 through n H max of n whole square. Okay, one very important, we're going to sketch the following, we're going to sketch the partial energies, okay, as a function of n. Remember, as n goes to infinity, all of them must converge to the same sum. Total energy is the same for all three of them. Okay, now the H of n, let us say, starts at 0 and then approaches the maximum. So this is E of n, the partial energy. So this is the energy plot with respect to as a function of n. Basically, you're plotting the part. So this when it reaches n tends to infinity, this will be equal to 1 over 2 pi integral minus pi to pi mod h e of j omega magnitude squared d omega. Okay, so basically the upper limit is reached. Now, if you plot the same partial response for the minimum phase system, what we find is that it does this. It reaches the maximum value much sooner. Okay, and if you look at so this is E min of n, and then the maximum phase term is the one that approaches it the slowest of the lot. And again, all of them will reach the same peak value. This is E max of n. Okay. Now, then it becomes very curious to say, what do the impulse responses look like, right? Because why is it that this particular behavior is present? So again, this is more of a what I would say is more of a conceptual diagram. So if the impulse response of the mixed transfer function, the transfer function of the mixed zeros, let us say, was given by a response that looks like this. It looks like the sinc function. Okay. Now, the response of the minimum phase transfer function, it has the same energy, total energy, but has got the following characteristic. It rises faster and then dies down. Okay, and the maximum phase, now you can see that when you convolve this particular impulse response with a input sequence, notice for the minimum phase term, this is h min of n. H min of n. See, the impulse response occurs in a much earlier, right, with respect to n. Therefore, the delay in getting the output is lower. That is why we say that the group delay for a minimum phase system is going to be less than the other. This is the mixed system h of n, and this is the maximum phase system h max of n. Okay, so some very interesting properties. So I have a transfer function. Some zeros are inside, some zeros are outside. Now, if I move all the zeros inside the unit circle, then I will get a minimum phase transfer function. In addition to being minimum phase, it has got the minimum group delay. That means the output will start appearing faster than in the other cases. And this also results in the partial energy of a minimum phase system being more than the partial energy of any of the other systems. So how can we write this particular result? We can write it in the following manner. Okay, we can say that the statement with regards to partial energy is that E min of n, partial energy at any index n, will be greater than or equal to the partial energy of the sequence of the transfer function with mixed zeros will be greater than or equal to E max of n. Okay, this is the general statement, and what we are interested in is the fact that this is the minimum group delay or minimum phase lag system, and therefore that is the one that is of interest to us, and that has got all of the zeros inside the unit circle. Okay. So, I hope you are comfortable with what has been the reason for us to study minimum phase, and where did we get the property of minimum phase? By using the property of all pass. What is the property of all pass? The property of a causal stable all pass is the phase response is monotone decreasing and the group delay is always positive. So, using those two properties, we have obtained these results. Now comes a very important result which you must always keep in mind. This result says any rational transfer function h of z that is causal and stable. Again, we all are only interested in causal and stable transfer functions. So, but let us specify that causal and stable h of z, any can be expressed, can always be expressed in the following form, where it can be expressed as h of z equal to h min of z. Okay, it's a minimum phase transfer function. It has got the same magnitude response as h of z. This multiplied by an all-pass transfer function HAP of z, where HAP is a causal stable all-pass transfer function. Okay, so basically you can always write it as a minimum phase transfer function times a all-pass transfer function. Okay, so here is an example which I would like you to look at, and then we can explain and apply it subsequently as well. Okay, so here is the a quick example that you can try out. Okay, example 1. Example 1 and 2 will look similar, but again the reason is I want you, it's more of a repetition. Okay, h of z equal to 1 minus C naught Z inverse, 1 minus C naught conjugate Z inverse divided by 1 minus 1/3 Z inverse, 1 minus 1/4 Z inverse. Okay, and we are given that C naught is equal to 3 by 2 e power j pi by 4. Okay, it is a 0 outside the unit circle at an angle plus pi by 4, and the conjugate will be at minus pi by 4. Okay, so obviously this is a causal stable transfer function. It is causal and stable. So we can tick off that part, but it is not minimum phase. So how do I write it in the form of a minimum phase transfer function? And I think that's a important way to do that. So here is what we are going to do. Take the numerator separately. 1 minus C naught Z inverse, 1 minus C naught conjugate Z inverse. Okay, and factor out the C naught from the first term, C naught conjugate from the second term. So what you will get is C naught conjugate magnitude squared. Okay, so maybe write it as 2 steps. Okay, so take it as minus C naught, then what you get is Z inverse minus 1 by C naught. Okay, I hope you are able to see that. Then you factor out minus C naught conjugate, then the second term becomes Z inverse minus 1 by C naught conjugate. Okay, so this becomes magnitude C naught squared, Z inverse minus 1 by C naught, Z inverse minus 1 by C naught conjugate. Okay, very important. So basically this is what we have been able to write down. Okay, so I want to take it one step further. Okay, so what we will do is we will write the all pass functions corresponding to this. Okay, how do we do that? Let's just take this to the next page. Okay, so I have this as my transfer function. I've just rewritten the numerator part, and I'm going to write this in the following form. Okay, I'm going to keep this as is, Z inverse by 1 minus C naught, Z inverse minus 1 by C naught conjugate. I'm going to divide by the poles at the reciprocal conjugate locations. Okay. So then what I have here is 1 minus 1 by C naught Z inverse, 1 minus 1 by C naught conjugate Z inverse. Okay. Notice that the zeros and poles are now at the reciprocal conjugate location of the zeros. Now I have divided by this, so I am going to multiply by the same quantity. 1 minus 1 by C naught Z inverse, 1 minus 1 by C naught conjugate Z inverse. Okay, so these two terms are equal. Of course, there is a magnitude C naught squared. Okay, so the original term, I pulled out C naught, obtained an expression, and then obtained multiplied and divided by the same quantity, but these quantities are the poles are located at the reciprocal conjugate location. Now, please verify that this is an all-pass transfer function. Okay, how do we verify that? Where are the zeros? Zeros at C naught conjugate. Okay, where are the poles at 1 by C naught conjugate, 1 by C naught, reciprocal conjugate location. So therefore, this is an all-pass function. Okay, this is verified. Now, this transfer function has got the zeros sitting inside the unit circle. How do I know that? Where are the zeros? Z inverse is equal to C naught. The zeros are at Z equal to 1 by C naught and 1 by C naught conjugate. Okay, and C naught was outside the unit circle, so 1 by C naught conjugate will be inside the unit circle. So these are at exactly the same locations as the original zeros, but now are sitting inside the unit circle. So I can call this as the minimum phase transfer function H min of Z. So the original transfer function H of Z, which was Z inverse, let me just make sure I make 1 minus C naught Z inverse, right? That was how it was, yeah. Okay, let me just copy paste this. Okay, this was the original transfer function. We have shown that it can be represented within a scale factor of a minimum phase transfer function which has got the same magnitude response multiplied by the all-pass transfer function. Okay, so they shouldn't call this as minimum phase. So this has got zeros inside the unit circle. Zeros inside unit circle. Okay, and so what will H min of Z be? Min of Z will be, it will be this numerator, 1 minus 1 by C naught Z inverse, 1 minus 1 by C naught conjugate Z inverse divided by the original denominator, 1 minus 1/3 Z inverse, 1 minus 1/4 Z inverse. Okay, so what we have shown is that H of Z arbitrary transfer function. It is causal and stable, so all poles inside the unit circle, you don't have to do any of the poles, but the zeros were outside the unit circle. Both zeros were outside. What we did was we reflected them to the reciprocal conjugate location to produce a minimum phase transfer function, and to compensate for the fact that you have reflected them inside, you produce a corresponding all-pass transfer function which was causal and stable, and therefore you are now able to represent h of z in terms of a as a product of a minimum phase and an all-pass term. Okay. Now let me maybe leave you with an exercise. You can it's very similar, so I suppose it's not necessary for us to do it, but this is something that I would like you to do. H of z is a transfer function which has got 4 zeros: 1 minus C1 z inverse, 1 minus C1 conjugate z inverse, 1 minus C2 z inverse, 1 minus C2 conjugate z inverse. Okay, we are given that C1 is at 0.9 e power j 0.6 pi. C2 is at 1.25 e power j 0.8 pi. Okay, one pair of zeros inside the unit circle, another pair outside the unit circle. Want you to factorize it in the form h min of z times h ap of z, and provide the expressions for h min of z. What is it? H ap of z. What is it? Okay, both of these you should be able to do it with the tools that we have. Identifying the zeros that are inside the unit circle, you leave them as is. The zeros that are outside the unit circle, you reflect inside and then create an all-pass transfer function, which you should be able to verify. Okay, just as a hint, let me just give you what the all-pass transfer function should be. This will be magnitude C2 squared z inverse minus 1 by C2, z inverse minus 1 by C2 conjugate divided by 1 minus 1 by C2 z inverse 1 minus 1 by C2 conjugate z inverse. Okay, so that will be the all-pass transfer function. Of course, the minimum phase transfer function, I'm sure you will be able to get it without much difficulty. Okay, so this more or less brings to an end our discussion in terms of the minimum phase transfer functions.